Hi, my name is Tuowen. I'm a PhD student at the University of Utah under Professor Mary Hall. My research interest is in the code generation and the polyhedral compilation methods related to data layout. This talk is on our work to improve the communication performance of Stencil application by optimizing unknown data movement during the communication using fine-grained data blocking. This work is done with our collaborators at Berkeley National Lab, Hans and Sam. It is supported by the Exascale Computing Project, and we use facilities at Oak Ridge National Lab and Argonne National Lab. When one look to this, Hi, my name is Tuowen. I'm a PhD student at the University of Utah under Professor Mary Hall. My research interest is in the code generation and the polyhedral compilation method related to data layout. This talk is on work to improve the communication performance of Stencil application by optimizing the unknown data movement during the communication using fine-grained data blocking. This work is done with our collaborators at the Berkeley National Lab, Hans and Sam. It is funded by the Exascale Computing Project, and we use facilities at the Oak Ridge National Lab and Argonne National Lab. When one looks to adapt a scientific application to large-scale problems or to achieve a better time to solution, one may distribute the computation to multiple nodes. However, when the computation is distributed, communication is often required to coordinate between these nodes and combine their results. When we look at the communication performance of a distributed Stencil application, we find that it may not be bounded by the network performance. And in fact, unknown data movement that's incurred during communication, such as packing, which is used to combine the data to form MPI messages, can potentially take up a majority of the time spent during communication. And here we show the result from a highly optimized MPI and OpenMP stencil framework for Intel platform that's called YASC. And then we find that even for rather large subdomains, such as 512 cube domains, the time spent doing packing is already greater than time spent for MPI communication. And in fact, as the subdomain gets smaller, the portion of the time that's spent to do packing gets even larger, up to 89% out of the whole computation loop. And because packing doesn't scale with either computation or MPI communication, it becomes a great factor to hinder the strong scaling potential of the Stencil application. In our work, we applied fine-grained data blocking to optimize the communication performance of Stencil applications. We used two methods, layout optimization and memory mapping with virtual memory, to optimize the unknown data movement that's incurred during communication, especially related to packing. These two methods are evaluated on both CPU and NVIDIA GPUs. Stencil computation is commonly employed to solve partial differential equations. It is characterized by its access pattern of computing the value of a point using nearby points. And here we have an illustration of a 2D 5-point stencil, where the value for the red cell is computed using the blue cells and the red cells from the previous iteration. And if we apply the stencil to a 4x4 subdomain, which is shown to the right, then for each iteration of this computation, it will be needing values from the blue cells, which are not part of the subdomain. In fact, the values of these blue cells will come from neighboring subdomains, and these blue cells will form the ghost of this subdomain, and the process of exchanging data from neighboring subdomains to these blue cells is the ghost exchange. And doing this ghost exchange in Stencil application, after we have defined the ghost we can also find the surface of the subdomain, which is the regions of data that needs to be sent to neighbors. And because there is only one unit stride direction, packing is often needed to collect data from non-contiguous chunks of memory into one message for each of the remote rank. And the process of packing is inefficient because it often incurs strided memory access, and because there are different size memory regions, and it's also difficult to parallelize. We also note that this communication pattern exhibits in ghost zone exchange have some common properties that is shared across many different applications. First is that the addresses and size of the data to be communicated is static for at least a few iterations. Second is that the data to be communicated is a subset of the data owned by the current rank. The last is that the data sent to different remote rank may overlap. The numbers shown in the right part of the figure that illustrate how many neighboring subdomains require that specific part of the data. The four corners are required by four different neighboring subdomains, while the edges are required by one remote subdomain. We believe that the cause for why packing is needed is because there is a disparity between the physical and the logical ordering of the data. We can define the physical ordering of the data as the layout that is expected for MPI communication. That is when one follows a memory pointer. And the logical ordering of the data is the layout used during computation, which encodes the relative position between data. And we believe we can solve this by adding indirection to manage the data in the application. We have done this to Stencil application in two ways. First, we applied fine-grained data blocking to the subdomains in the Stencil application, and we added a second layer of indirection using virtual memory mapping. We have an fine-grained data blocking implementation for Stencil application that we call bricks, where it's a decomposition of a subdomain to fixed size bricks, and each of the brick is stored contiguously in memory without any per brick ghost cells. And we have shown in our previous work that this can greatly improve the computation performance of a Stencil application by eliminating data streams during the computation. This can greatly optimize the vertical data movement by improving cache and TLB behavior. And when bricks are combined to form a subdomain, they are first stored consecutively in memory by their index, and the neighboring information which describes in this subdomain which brick is to the left of which other brick is instead stored in an adjacency list. So this structure allows us to have an indirection from the logical to the physical layout. It also means that we can have a logical layout that is different than the physical layout. And below we show an 1D example where the physical layout is 0, 1, 2, 3, and the logical layout is 0, 2, 1, 3, 0. And this transformation of applying bricks to the data using Stencil application can be viewed as transformation from arrays, which is structured data, into fine-grained data blocks bricks that is also structured, and adjacency lists, which describe the neighboring information that have some unstructuredness in it. After we have applied fine-grained data blocking to the subdomain of a stencil application, we can also tag values on the surface by which neighboring subdomain requires them. And this allows us to identify regions on the surface and in the ghost zone by grouping the data that are always sent together. And these regions should be located consecutively in memory because they always move as a unit. And we also note that how these regions are stored in memory will affect how many messages is required to communicate without doing any packing. For example, we have the subdomain below requiring the data from region 1, 2, 3 on the surface. And because 1, 2, 3 are stored consecutively in memory, only one message is required. However, because 1, 4, 6 is required by the subdomain to the left, however, 1, 4, 6 are not stored consecutively in memory, then it will require 3 different messages to send it. That is, without doing any packing. Thus, we have the goal of layout optimization is to reorder these surface regions so that without doing any packing, we can try to minimize the number of messages. Under these conditions, we can produce optimized layout for 2D, which requires 9 messages to communicate, and also optimized layout for 3D, which requires 42 messages to communicate. And we're also able to prove a lower bound on the number of messages for ND subdomains that is proportional to 5 to the nth power over 3. So if we compare to the number of neighbors, which is also the number of messages required with packing, then layout optimization is obviously more efficient when the number of dimensions are small. However, if we compare to packing, layout optimization firstly doesn't need the packing operation that incurs the huge cost that we shown earlier, but it does need to add a few startup time for a few extra messages. However, the communication volume with either packing or layout optimization is the same. And then after, we can add another layer of indirection in the form of memory mapping. This is using the virtual memory space, which we can map to the physical memory using mmap calls. And this process also allows us to create shared mapping, where one physical region can be mapped multiple times. And this allows a piece of data to appear multiple times in memory, which means that non-contiguous regions in the physical memory can be made contiguous if we map them consecutively in the virtual memory. And below we illustrate one example that region 1, 4, 6 is made contiguous by mapping them consecutively after pointer left, so that when MPI is called on pointer left, these 3 regions appear to be consecutive. And with this, then no extra message is needed. We also explored how our method can work on NVIDIA GPUs. And for GPU applications, it involves a more complex communication process, because not only did it need to manage data on the host, but it also need to manage data in the GPU. And also depending on the choice of the communication method, may also require to explicitly moving data between CPU and GPU. There is also many available choices when writing the communication for GPU application. One can choose to do packing and unpacking on the CPU or on GPU, or one can leverage technologies like CUDA-aware MPI or Unified Memory System Allocator to move the data implicitly between the host and GPU. With fine-grained data blocking, we're able to avoid unnecessary data movement because the internal regions can be made separate from the surface and the ghost zone, so that if only the surface is needed for communication, then the internals and the ghost zone doesn't need to be touched. With layout optimization on the GPU, one can use CUDA-aware MPI to avoid manual CPU-GPU data movement, and depending on the implementation of the MPI, it may also use RDMA with GPU Direct. And currently, there are two ways to employ memory mapping on the GPU. One is to use a more recent feature of CUDA that's called low-level GPU virtual memory management, which is not available on our platform and we weren't able to test it. And the second is to use unified memory with system allocator. And with the second, it supports implicitly moving data between CPU and GPU using the page migration mechanism. We're able to test our method on two large-scale supercomputer. One is the Theta supercomputer using the Intel Xeon Phi nodes, and the other is a Summit supercomputer with IBM Power 9 CPUs and NVIDIA V100 GPUs. We tested our method using two synthetic 3D stencils. One is a 7-point stencil, which represents a more memory-bound stencil, and the second is a 125-point stencil that represents a more compute-bound stencil, whose result is shown in the paper. This figure demonstrates the CPU performance using a 3D 7-point stencil, where the domain is decomposed into 2 by 2 by 2 subdomains on 8 different theta nodes. And when we vary the subdomain on each of the nodes, we're able to evaluate the communication performance with respect to different surface volume ratio under ideal network condition. And if we move from large subdomains to smaller subdomains, it is also a proxy to strong scaling. And our method, layout, and memory mapping is able to achieve up to 14.4 times better communication performance compared to YASC because we don't do any packing. And we're also able to achieve performance very close to the network performance, which represented communication on message size buffers. This figure shows the communication performance on the GPU. And as we mentioned before, there are two ways to avoid explicitly moving data between CPU and GPU. One is to use CUDA-aware MPI represented using CA, and the other is to use unified memory with system allocator represented with UM. And this figure uses a similar setup as the experiment on the CPU, where we decompose a cubical domain into 8 cubical subdomains distributed across 8 summit nodes. And we only use one GPU on each of the summit node so that the subdomain on each of the GPU is also cubical. And we find that layout optimization with CUDA-aware MPI achieves the best performance that is very close to network performance using CUDA-aware MPI. That is to communicate the message size buffers with the CUDA-aware MPI. And layout optimization with unified memory is a bit slower because it is moving data implicitly between CPU and GPU. And memory mapping with unified memory is slower still because they also require some padding to align the regions on the surface and in the ghost zone to page boundaries. However, MPI types with unified memory is the slowest in the result that is shown. And we are able to achieve up to 13.8 times faster if we're comparing between layout optimization using CUDA-aware MPI and MPI types with unified memory. And layout with CUDA-aware MPI is able to achieve up to 13.8 times better performance compared to MPI types. In summary, this work uses indirection to manage unknown data movement, especially related to packing during communication. We use two methods, layout optimization and memory mapping with virtual memory. And we were able to significantly improve the communication performance on CPU and the NVIDIA GPU. So here we show the strong scaling result using memory mapping on the Theta supercomputer, where we scale 1024 cube domains from 8 nodes to 1024 node, which represented a quarter of the Theta supercomputer. And we can see that even though YASC stopped scaling at 512 node, we scaled until 1024 node. And if you look at the trend, we are expected to continue scaling. And we obtained up to 9.3 times faster at 1024 node. In conclusion, we believe that data layout with indirection, especially layouts such as bricks that have mixed structured and unstructuredness, is an important abstraction to achieve performance portability because it can optimize both the vertical and horizontal data movement. Thank you for listening to this talk.